Hey, mathletes. What we're going to look at here in example number one is a type of question known as a related rate. So what do we have here? Air is pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right. This is known as a related rate. So how do I know the difference between this and, say, a max-min question? Well, in a max-min question, I'm usually going to hear the words or read the words maximum or minimum. Find the maximum area, find the minimum area, right? What's happening here, what I'm reading is this. It says the volume is increasing at this rate. So what is this? What do I know? Well, what I know is the volume is increasing. So the volume with respect to time is changing. So remember, D means delta. It means change. So it means the change in volume over the change in time is positive 100 centimeters cubed per second. Then it says how fast. So that's what I want, right? How fast? So what do I want? Well, I want how fast is the radius changing? So I've got dr dt. How fast is the radius changing? But the radius is changing at not at a constant rate. It's going to be changing. It's dynamic depending on how big the balloon is. So whenever we're looking for something, it's going to be at a specific moment. So when the diameter is 50, well, that's when the radius is 25 centimeters. So what I'm always going to do first is I'm going to write down what I know and what I want. Then what I'm going to say to myself is, hey, is there a formula that I know that helps me with these questions? Well, this is the volume of a spherical balloon. Well, I know that. Volume is 4/3 pi r cubed. Now what I say to myself, okay, I know what I know what I know. I know what I want. I have a formula. And before I start, I need to take the derivative here because I need to get this with respect to time. But before I do that, I say to myself, okay, if I go and take the derivative, what will I get? Well, if I take the derivative of v, I'll get dv dt. Perfect, I know it. The derivative of 4/3 and pi is a constant, so no big deal there. And the derivative of r is dr dt. So what I'm analyzing here, friends, is before I take the derivative, do I have everything I need or is there anything missing? Okay, I'm good to go. Now I take my derivative with respect to time. So the change in volume with respect to time is 4/3 pi times 3r squared. And we have to implicitly differentiate because we're with respect to time, not with respect to r. Okay, take the derivative. It's looking pretty to me. Now what I'm going to do, friends, is simply just start subbing in what I know. Okay, and I'm not going to include my units, right? That's science class's problem. Times, well, I could even right here, if you wanted to do that first, maybe that would have been good. Okay, the radius, this is where I input the radius. Notice I didn't put it in the original formula because the radius is changing. It's dynamic. It's constantly changing. So I don't sub in that 25 until after I've taken the derivative. Now, friends, all I've got to do is just figure out what the heck is dr dt. Like I just got to rearrange at this point, right? So what is this? 100 is equal to 25 squared is, I think, 625 times 4. So that's 2,500. And I'm going to leave the pi there, right? I like to leave things in exact values. I like to do this without a calculator. And because at some point in your life, you know, if you go on to university and take some higher level calc, you might not get to use a calculator, which is kind of a scary idea. But look, we didn't really need it here at all. And then I'm just going to simplify that down. So the change in radius with respect to time is 1/25 pi. And now I'm going to put my units back in. This is centimeters per second. And it doesn't hurt to write a sentence at the end. The radius is increasing. I'll write it. I won't be lazy. The radius is increasing at a rate of 1/25 pi centimeters per second. But that's not specific enough, friends. It's not always increasing at that rate. Specifically, when the radius or I could have talked about the diameter, but when the radius is 25 centimeters. Okay, at any other moment when the radius is a different size, it's going to be increasing at a different rate. So again, what I do, friends, every time I write down what I know, what I want, I write down my formula. I think before I take the derivative, is there anything I'm missing that I got to go and hunt for? And then all it is substitute in and solve. Okay, there's kind of, I would classify this as a geometric sort of related rate. We'll go through some more examples and you can see some more types in just the next examples.